In today's video, we'll be looking at one of the important properties discussed in chapter 1, that is Euclid's division lemma. If you have not seen part 1 video of chapter 1, I would request you to first check out that video so that you would get a brief understanding of what we are going to study in chapter 1. I have put the link in the description below. You can see that. So now let's start with Euclid's division lemma. A lemma is a proven statement used for proving another statement. Before we get deep understanding about the Euclid's division lemma, let's solve some of the problems related to HCF. You'd get to know why I am solving problems related to HCF within few minutes. So we all know that HCF means highest common factor. Let's try to find out HCF of two numbers, that is 5 and 10. So first what we are supposed to do is factor. We are supposed to find. So factors of 5 and 10. Factors of 5 are 1 and 5. And factor is that number which divides another number. We know that 1 divides 5. So 1 is a factor of 5. And 5 divides 5. So 5 is also a factor of 5. And factors of 10 will be 1, 2, because 2 divides 10. And 1 divides 10. 3 does not divide 10, so 3 is not factor of 10. 4 also does not divide 10, so 4 is not factor of 10. Again 5 divides 10, so 5 is factor of 10. And then finally we have 10 number itself as its factor, because every number is factor of its own, and we all know that. So now we have found out the factor. Now we have to find what is common between these factors. The common things here are 1 and 5, right? So we'll write down here. So 1 and 5 is common. Now we have to find what is highest. We can clearly see that 5 is the highest number among 1 and 5. So 5 will be HCF of 5 and 10. I have mentioned this HCF of 5 and 10, the numbers in the bracket, that's the only difference. So now this is fine if we have small numbers like this 5 and 10. But what if we have a huge numbers like 1052 and 25? You cannot just write down factors like this, right? For 1052 it will take a lot of time. So what we will do is we will use long division method. And always remember, whenever you do long division method, start it from the leftmost side of the page so that you get sufficient page on the right side. So now 25 4s are 100 and the remainder is 5, and we'll get this 2 down over here, so 2. And in long division method, one rule is we will continue long division method till remainder equals 0. So I hope this everyone knows, right? And here 25 2s are 50, so 2 will be the remainder. This is remainder, and we know that this remainder is not equal to 0. So we again continue the process. We will get this 25 divisor over here as dividend. So 2 1s are 2, 0. We will get this 5 down here. So 2 2s are 4. Then we have 1 as a remainder, and this is not equal to 0. So we again continue this process. We will get this 2 excuse me over here. So 1 2s are 2, and we can see that this remainder equals to 0. And when this remainder equals 0, we stop our division method, and whatever the divisor will be there over here, that will be our HCF, right? So 1 is our HCF. So can you notice something connection between this dividend, divisor, quotient and remainder? Just see if you can find some relation between these four things. Let's try that. So is 1052 equals 25 into 42 plus 2? Is this true? Let's check out. So 25 into 42 will be 1050 and plus 2, and this equals 1052, and this is true. So can we just say that this dividend, this is quotient, this as divisor, and this is remainder. So can we just say that dividend equals divisor into quotient plus remainder? Yes, of course we can say that, because we have seen here this holds good completely fine. So we can say that we'll mention dividend as A, divisor as B, quotient as Q, remainder as R. So we can say that A is equals to BQ plus R. For a condition of R, what? R should be greater than or equal to 0 and it should be less than divisor, that is B. Right? So this is what interestingly called Euclid's division lemma. Easy, right? Yeah. So this whole statement is called as whole equation is called as Euclid's division lemma. So now let's look at the statement given. Euclid's division lemma is a given positive integers a and b. There exist unique integers q and r satisfying this condition. So that is what we have written here. So I hope now everyone is clear with what is Euclid's division lemma is. So now let's move on to the next topic, that is Euclid's division algorithm. So Euclid's division algorithm is based on this lemma itself. So algorithm is basically what? An algorithm is a series of well-defined steps which gives a procedure for solving a type of problem. So now let's see how we can solve this in the form of algorithm. See here, the problem, it says that gives a procedure for solving a type of problem, right? So the problem for us here was finding HCF, and we found HCF using this whole long division process, right? This whole long division process. So when we write this in the form of steps, this is called as algorithm. So can we just name this as step 1, and next step 2 will be, consider this next process, this 2, 25, 12 and 1. So we can write that as 25 equals 12 into 2 plus 1. This will be our step 2, and finally we have in the last process this 1, 2, 2 and this 0. So that will be this 2 equals 1 into 2 plus 0, and this will be our step 3, right? So all these 3 steps together makes Euclid's division algorithm. Easy, right? So now we have studied about Euclid's division lemma, that is over here, and we have studied about Euclid's division algorithm, that is these 3 steps. So now let's see what they have given in the textbook about Euclid's division algorithm. So they say that to obtain the HCF of 2 positive integers, say a and b, with a greater than b, follow the steps below. Step 1. Apply Euclid's division lemma to a and b. So we find the whole numbers q and r such that a is equals to bq plus r, and the condition for r is this. Step 2. If r equals 0, b is HCF of c and d. If r is not equal to 0, apply division lemma to b and r. In step 3, continue the process till remainder is 0. The divisor at this stage will be required HCF. So that's what we have done here, right? We have first done it in the form of long division method, then we have written the steps over here. in exam, whenever you get this kind of problem, it becomes very easy. First you apply this long division method in the rough. Just solve this problem in the form of long division method in the rough side of the page, and then write it in these steps, like step 1, step 2 and step 3. Here we have discussed, right? And then it becomes very easy. So we have applied the division for 1052 and 25. We got a remainder as 2 over here, that was not equal to 0. So again we continued, and then we got remainder as 1, that was also not equal to 0. Then we continued and we finally got remainder as 1. And what they say here, see, continue the process till remainder is 0. The divisor at this stage will be the required HCF. So the divisor, this is our divisor, right, for this process. So this will be our divisor for this process. So divisor at this stage, whenever the remainder becomes 0, the divisor at that stage, that is 1, is HCF of our numbers. So we can see HCF of 25 and 1052 is 1. So this is clear, right? All examples given in the textbook. So the first example is, use Euclid's algorithm to find HCF of 4052 and 12576. As we discussed before also, first what we are going to do is, first we are going to solve it by long division method. Then we are going to write down in the form of steps given here, so that it becomes easy to write down in the form of steps. So first let's solve it in the form of long division. So the number given here are 4052 and 12576. So 4052 3s are 12156. So when we solve this, we get 420. And then when we continue, we know that the remainder is not equal to 0. So we again continue this process. We take this 4052 over here as a dividend over here, and then 420 into 9 is 3780. Then we continue the process, and again here we can see that remainder is not equal to 0. So again we continue the process. Then we consider this 420 over here, and then we continue. 272 into 1s are 272, and the remainder here is 148, and again this is not equal to 0. So we continue this process in this way, as you can see here, and finally we get here remainder equals to 0, and divisor at this place for this whole process, divisor is 4, and this is HCF of the given number. So now how to write this in the form of steps, let's see. Okay, so first step 1, since 12576 is greater than 4052, we apply division lemma. See, since we are writing it in the form of A is equals to BQ plus R, we mention here that we are applying division lemma to these numbers. And to get what? See, here divisor, it's a dividend, divisor, quotient, remainder. I'll mention it as R, this as Q, this as A, then this as B. So we can say that A is equals to BQ plus R, right? So that's what they have done here. See, A is this one, 12576, B is 4052, Q is 3 into 3 plus this remainder R. So this is R. So again we continued this process, right? So again they're writing it in the step 2. Step 2 is, since remainder 420, here we have mentioned, right, 420 is not equal to 0, we apply division lemma to. Now for what we are going to apply, we are applying for this 420 and 4052. So that's what they have mentioned to get this. So now they are considering this portion. So now they have written here 4052 equals 4020 into this 9 plus this remainder, and again remainder is not, so you can just write that same sentence whatever you have written in step 2. Since the remainder here, you should just write 272 is not equal to 0, we apply division lemma to. Here we will apply division lemma to 272 and 420. That's what they have done here. See, for this they have considered it this way. Wait a minute. So here this whole step, whatever I have marked in the right. For this they have applied 272, 421 and 148. So 420 equals 272 into 1 plus 148. That's what they have done here, right? 420 equals 272 into 1 plus 148. So now that is done, and again remainder is not equal to 0, so we again just continue the process with 148 and 272, and this is again the next step. So here we will write it as 272 equals 148 into 1 plus 124, this step. That's what they have written. See here, 272 equals 148 into 1 plus 124. Now since again the remainder is not equal to 0, we again continue for this stage. So here you can see I am marking it. So here what happens, 148 equals 124 into 1 plus 24, right? Now see here, that's what they have written. 148 equals 124 into 1 plus 24. I hope this is understandable to everyone. If you have any doubts, please post it in the comment section and I'll try answering them. Then next step here is (24), 124, 5 and 4. So this can be written as 124 equals 5 into 24 plus 4. So here you can see 124, that's what we have done here, right? Wait, let me minimize. So here see this thing, and here same, right? Yeah. Then next final step that we have here in marked in the blue color. So you can just see that can be written as 24 equals 6 into 4 plus 0, right? Let's see here, 24 equals 6 into 4 plus 0, right? I hope this is clear how they have written all these steps, and this is clear. And finally what you should write very importantly is the remainder has now become 0, so our procedure stops. Since the divisor at this stage is 4, HCF of these two number is 4. That's what, right? Here we have seen HCF is 4. That's it. So I hope this problem is clear to everyone. First let us quickly revise this. So first thing is you have to solve this in the long division method. Step 1 is long division, and step 2 is write in form of Euclid's division lemma. And the lemma equation is A is equals to BQ plus R, and condition for remainder is this. So I hope this whole problem is clear now. So now let's move on to the second example given in the textbook. So that is, show that every positive even integer is of form 2q and that every positive odd integer is of form 2q plus 1 where q is some integer. So first thing what you have to see here is even integer is of form what? Even integer is of form 2q and odd integer is of form 2q plus 1, right? And what was our Euclid's division lemma equation? A is equals to BQ plus R, right? So now let's see the solution. Let A be any positive integer and B equals 2. A be any positive integer and B they have mentioned it as 2. So this will be A is equals to 2q plus r. Right. Then by Euclid's algorithm, a is equals to 2q plus r. That's what we have written here. For some integer q is greater than 0 and r equals 0 or r equals 1. Here what they have taken is r equals 0 or r equals 1. They have taken this because we know the condition that r should be in the range of 0. R should be greater than or equal to 0 and it should be less than b, and our b here is 2, right? So they have took it as 0 less than or equal to r and then less than b, that is 2. So they have mentioned it here because this is the condition. So when we substitute this condition of r, let's name this as equation 2, this as equation 1, equation 1, equation 2. Now substitute equation 2 in equation 1. What do we get? If for this we will have r equals 0 and 1. We cannot take 2 because this is less than 2, not equals to 2. So for this r will be 0 or 1. So we can write it as a is equals to 2q. Here r equals 0. A equals 2q plus 1. Here r equals 1. These two things will come out. So let's see here. That's what they have written. A is equals to 2q or 2q plus 1. Right. Now if a is of a form 2q, then a is an even integer because it is a multiple of 2. And we know that anything which is multiple of 2 is an even integer. Also a positive integer can be either even or odd. Therefore any positive odd integer is of form 2q plus 1. Because here we have this 1 as extra, this will be even part and this will be, whenever we add even number with 1 we will get as odd. We all know that, right? So we say that therefore any positive odd integer is of form 2q plus 1 and even integer is of form 2q. So I hope this is clear to everyone now. If you have any doubts, please ask in the comment section and I will try to answer the doubts. Let's see the third question. What it says is, show that any positive odd integer is of form 4q plus 1 or 4q plus 3 where q is some integer. It is same just like our previous problem. See here what they have asked is, they have asked in form of 2q plus 1, but here they have asked in the form of 4q plus 1 or 4q plus 3, right? So what is Euclid's division lemma? First write down that. It says that a is equals to bq plus r and condition for r is it should be greater than or equal to 0 and less than b. What is b? B is our divisor, right? So here let's take b as, let b equals 4. Why are we taking 4? Why not any other number? Because they have asked here, see, when you just compare this equation with this, you can see that b here is 4, right? So, and here also if you see in this equation 4q plus 3, you can see it is 4 over here. So we are taking b as 4. Then next let's substitute. Before substituting, let's check what will be the condition of r. If b equals 4, then we'll just write down here r should be greater than or equal to 0 and r should be less than b, and our b is 4 and r, so therefore r will be 0. So it should be here 4, right? Yeah. So it will be 4. Yeah. So r equals 0, 1, 2, 3. Since it is less than 4, we are not considering it for considering 4. So we'll just consider r from 0 to 3. So now let's write a Euclid's division lemma for r equals all these values and b equals this value. So the first one for r equals 0 will be a is equals to 4q plus 0. I will not be writing plus 0 because it's same as 4q only. Then next, when r equals 1, it will be 4q plus 1. I'll just write here condition. This is second equation. Here r equals 1 and b equals 4. For understanding, I'm just writing that. Next, a equals 4q plus 2. This will be our third equation. Here r is what? 2. B is 4. Then final last one will be 4q plus 3. Fourth equation. R is 3 here and B is 4. Right. So I hope this is clear to everyone now. Now let's see what they have given in the solution. Let us start with taking a, where a is an odd positive integer. We apply the division algorithm with a and b equals 4. That's what we have done here. B equals 4 we have applied. Then they have given here conditions. Since r is in range from 0 to 4, the possible remainders are 0, 1, 2 and 3. That's what we have done here. 0, 1, 2 and 3. Then what they say is, that is a can be 4q or 4q plus 1, 4q plus 2 or 4q plus 3. That's what we have done here. You can see it. These are possible values, right? Then where q is a quotient, and here we have considered it as a quotient from our Euclid's division lemma. Since a is odd, a cannot be 4q or 4q plus 2. See, what we can say is, they are considering a as odd, right? In question C, they have shown that any positive odd integer is of form this. So this cannot be odd. Why? Let's see that. See, if we consider a equals 4q, what do you mean by odd integer? First let's check that. Odd integer is something which is not divisible by 2. So now if we divide this by 2, so 2 ones are 2, 2s are 4, right? So 2q. So it is divisible by 2. So this is even. Next, let's check for the second equation. For a equals 4q plus 1. This is not divisible by 2. 4q plus 1 is odd. Why? Because, I'll write because as BCZ in short form. Because not divisible by 2, right? Next, let's look at this third equation. What it says, a is equals to 4q plus 2. So this is a multiple of 2. How? See, if we take 2 as common outside, we will be left out with 2q plus 1. So it is divisible by 2, right? So we say this as even. And finally we have a is equals to 4q plus 3. This is also not divisible by 2 because we cannot take anything as common here. Like in the above equation, whatever we took 2 as common, we cannot take here. So it is not divisible by 2 and it is odd. So I hope now you are clear why these two equations are even and these two are odd. That's what they are saying here. Since they are not divisible by 2. Since these things are not divisible by 2, they are considered as odd. Therefore, any odd integer is of the form 4q plus 3. Odd integer is of form 4q plus 1 and 4q plus 3. So, I hope this was clear why they have said any positive odd integer is of form 4q plus 1 or 4q plus 3. So now let's move to the next question given in your Ncert book. Fourth question. What they say is, a sweet seller has 420 Kaju Barfis and 130 badam burfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What is the number of that can be placed in each stack for that purpose? And always remember one thing, whenever you read question, first you have to know what is given, what are they expecting to answer from you. So what they have given here is 420 kaju burfis and 130 badam burfis. So first let's write down that so that your 50% of problem will be solved. 130 badam burfis. Next, what are they asking? She wants to stack them in such a way that each stack has the same number and they can take up the least area of the tray. What are they expecting? Least area, same number. What is the number of that can be placed in each stack for the purpose? Least area, it should be there, same number, it should be there, and what are they expecting? What is that number? So here in picture you can see, now we have a stack of badam burfis and kaju burfis. Here we have kaju burfis and here we have badam burfis. Now they are stacked in such a way that they should have a same number of burfis in each stack. So what we are supposed to do is we can just find it using a trial and error method. That's not the issue, but if you want to do it systematically, then we are going to solve it using HCF. Why HCF? Because they have asked to find it should take a least area of the tray, right? That's the reason we are finding it using HCF. So HCF of what given is what? 420 kaju burfis and 130 badam burfis. So HCF of 420 and 130. I hope this is clear now. So always what we have discussed is, whenever we get this HCF kind of a problem, first we will solve it using long division method and then we'll write it in the form of Euclid's division lemma. So now let's start with long division. So 130 3s, let's try 130 into 3, 390. Let's try 130 into 4, 520, which is bigger, so we are not considering this and we are considering this. So it is 390, 0, and we have 3 over here. Next, what we discussed, this divisor will become dividend for next step. So 34s 120, 35s 150. This is not considered, this is considered 4s 120, right? The remainder is 10, which is not equal to 0. So again we continue the process, we get this 30 down over here. So 10 3s 30, and the remainder over here is 0. So whatever divisor will be there at this stage will be our HCF, right? So HCF of 420 and 130 is 10. So how many burfis she can stack so that they have each number, same number in each stack, and they take a least space, that is 10. Right, now let's see the solution, whatever they have given in your textbook. So what they say is this can be done by trial and error method, but to do it systematically we find HCF of 420 and 130. That's what we have done now, right? Then this number will give the maximum number of burfis in each stack, and the number of stacks will then be the least. The area of the tray that is used up will be the least. So that's what we have discussed now. So they have done it using Euclid's algorithm to find HCF. So that's what we have also done here using long division method, and now we have to write it in the form of Euclid's division method. So now let's start. Okay, so first we'll write what is general formula of Euclid's division lemma. A is equals to BQ plus R, and condition for R is it should be greater than or equal to 0 and less than B. So now for this first stage, let me change color of pen so that you get to know. So first stage will be this one. For this it will be 420 equals 130 into 3 plus 30, and now here remainder is again not equal to 0. So again we continue the process. The second stage will be this that is 130 equals 30 into 4 plus 10. And final stage is this, right? Because here remainder becomes 0, so we write it as 30 equals 10 into 3 plus 0, right? These are the 3 steps in which we solve this problem. So let's look at the solution now. So yeah, that's what even they have done. They have solved it in the 3 steps. So the HCF, you can just compare these 3 steps with, let me minimize so that it becomes easy for you to check. No, it's still not, both cannot be seen in the same page. So yeah, you can just see here 420 equals 130 into 3 plus 30, the first equation. The second one is 130 equals 30 into 4 plus 10, that's what we have written over here. And the final step is 30 equals 10 into 3 plus 0, and that's over here. So yeah, now what they have written is, so HCF of 420 and 130 is 10, that's what we have mentioned over here. So for 420 and t equals 10, therefore this you should just write down this statement at the end of your answer, so that evaluator gets to know what is your answer at the end. Therefore the sweet seller can make stacks of 10 for both kinds of burfis. So I hope this problem was clear to everyone. Now let's start with exercise 1.1. So the first question, what it says is, use Euclid's division algorithm to find HCF of 135 and 225. So what we first learnt is, whenever we are asked to solve this Euclid's division algorithm in rough side of the page, what we will do, we'll first solve it using long division method, right? So 135 is smaller than 225, so this will be our divisor, this will be our dividend, right? So 135 and 225 we have. So 135 ones are 135, 0 we have, and then we have here 9, and remainder is still not equal to 0, so we continue the process. 135, whatever was here a divisor will become dividend over here. So now 90 ones are 90, 5 will be the remainder, and then we have over here 45, and this is also not equal to 0. So again we continue the process. Whatever here will be the divisor, that is 90 over here, will become dividend here. So 90 will write here, and 45 2s are 90, and here we can see that remainder equals 0. So whatever we get divisor at this part will be our HCF. So now let's write Euclid's division algorithm for this. So first question, first part, so Euclid's division algorithm to find HCF of 135 and 225. First we will consider this stage. So how we can write is, we know that Euclid's division algorithm is A is equals to BQ plus R, and condition for R is R should be greater than or equal to 0 and less than B, right? So what is our A here? That is 225 equals 135 into 1 plus 90, right? So the next step will be this stage. Okay, so we can write this in the form of Euclid's division lemma in this form. So 135 equals 90 into 1 plus 45, and the final stage is this. Here you can see. So this can be written as 90 equals 45 into 2 plus 0. And finally what you have to write is HCF of 135 and 225 equals 45. Easy, right? So I hope this was clear to everyone. And next let's see what question we have. So this is done, and these two questions, that is second and third, just write on yourself. If you get the answer, very well and good, and if you do not get the answer, then we will be seeing these two questions in part 4 video, where we will be solving important questions that have already appeared in your previous exams, previous year sample papers and board exams. Okay, so now let's move on to the second question. Let's read the question first. What it says is, show that any positive odd integer is of form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. We have already seen similar kind of problem, but still let's solve this problem. Okay, so second problem is, first let's write Euclid's division lemma. What it says, Euclid's division lemma. So we know that it says a is equals to bq plus r, and condition for r is should be greater than or equal to 0 and should be less than b. This is the only thing around which everything revolves in this particular property. Okay, in this Euclid's division lemma property. So now what they have asked is to show that positive integer is of form 6q plus 1, 6q plus 3 or 6q plus 5. So here can you notice something like it is in the b is 6 here, see here 6q, 6q, 6q. So we can say that, let us consider b equals 6. So if b is 6, let's check condition for r. So it will be like greater than 0, greater than or equal to 0 and should be less than 6. So r will take value from 0, 1, 2, 3, 4, 5, right? R cannot take a value of 6 because it's not equal to 6. It should be less than 6. So now let's substitute for all these values. So a will be, a equals 6q plus 0, for r equals 0 and b equals 6. So if we substitute this way for all particular values of r, let's check what we get. B equals 6 and a equals 6q plus 2, r equals 2 and b is 6, and a equals 6q plus 3 for r equals 3 and b equals 6, a equals 6q plus 4, r is 4 here and b is 6. Same thing for r equals 5 and r equals 6, right? So here in this, let us name this as equation 1, 2, 3, 4, 5, 6 and 7. Okay, so in first equation it is written as a equals 6q. Is this divisible by 2? 2 ones are 2 3s are, and q can be anything, right? So we'll just write q as the same way. So it is divisible by 2, so it is an even integer and we say it even. The next one, the second equation, is it divisible by 2? No, it is not divisible by 2, so it is called as odd integer, right? So let me write here odd. And is third equation divisible by 2? Yes, it is divisible by 2. See, if you consider a equals 6q plus 2, if you take 2 as common, then you will be left out with 3q plus 1, right? And 2, it is divisible by 2. So if you divide it by 2, yes, it is divisible. So this third equation is even. Okay, and fourth is again not divisible, so it is odd. Fifth equation is divisible, this is even. Sixth is not divisible, so it is odd, and this is divisible, so it is even. So now let's write down what are the odd positive integers we have got. That is the second equation, fourth equation, and sixth equation, right? So for a equals 6q plus 1, a equals 6q plus 3, and a equals 6q plus 5, they are called as odd integers, positive odd integers. So that's what they have asked in the question itself, right? Show that any positive odd integer is of form 6q plus 1 or 6q plus 3 and 6q plus 5 where q is some integer, and we have shown that these are positive odd integers. So I hope you understood this question. So now let's move on to the third question. First let's read the question. What they say is, an army contingent is of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in a same number of columns. What is the maximum number of columns in which they can march? So let's try solving this problem. First we'll just write down what is given. Okay. So 616 members of army contingent, right? 616 members army contingent, and army band is of 32 members. So 32 members army band. Let's understand the question. Okay, so you have your army band which is of 32 members, and you have here a very huge number of contingent people. Contingent, I hope spelling is right. Yeah, contingent, and they are of 616 members. They are supposed to march in equal number of columns. Like see, they have to march in this way, right? So how many columns should they march is what they're asking the question, right? They're asking what is the maximum number of columns in which they can march. So if you want to find maximum, then we have to find HCF. HCF of what? HCF of army contingent and army band, that is 616 and 32. 616 and 32, right? So let's start a long division method. 32 and 616. So 32 2s are 64, which is greater than the 61. So we'll just take 1s are 32 and we'll be left out with 9 2, and 6 is still remaining, so we'll bring this down 6 over here, and 32 into 10s are, we know it is 320, which is greater than 296. So let's try with 32 9s are 18, 9 3s are 27 plus 128. So 9s are 288, and the remainder will be 8, which is not equal to 0. So again we continue with our long division process. 4s are 32 and the remainder is 0 over here. So the divisor of this stage will be our HCF. HCF of 616 and 32 will be 8. So they have to march in 8 columns so they can maintain equal number of columns, right? So what is the maximum number of columns in which they can march? So I have to say the maximum number of columns in which they can march is 8. So I hope this is also clear. We have solved third question. So now let's move to the fourth question. First let's read the question. The question is, use Euclid's division lemma to show that square of any positive integer is either of form 3m or 3m plus 1 for some integer m. Okay, let's solve this question now. So the fourth question, they have asked to use Euclid's division lemma to show that square of any positive integer is of form 3m or 3m plus 1 for some integer m. Right. So what does Euclid's division lemma says? First we have to write that. That is a is equals to bq plus r, and condition for r is r should be greater than or equal to 0 and should be less than b. Right. So now let's take b as 3. Okay. So if we start this, then we'll get a is equals to, and for that r will be 0, 1, 2. A, and now if we write a Euclid's division lemma for these two conditions, we'll get a is equals to 3q for r equals 0, a equals 3q plus 1 for r equals 1, a equals 3q plus 2 for r equals 2. So now what they have asked is, they have asked to show that square of any positive integer is either of form 3m or 3m plus 1. So now let's square this. Okay, first let's name these equations 1, 2 and 3. So on squaring equation 1, what we get? A square equals 9 square. Now we have to represent it in the form of 3m, where m is some positive integer, okay. So we can write it as 3 into 3q square. See, if q can be any value, okay. So whenever you substitute any value to q, you are going to get an integer. So can we just say that this whole thing, this 3q square will be some integer which we will name it as m? So can we just write it as 3m? Yes, of course we can write. So we can say that according to the question, square of any positive integer is of form 3m. Now let's square the second equation. This is for equation 1. Okay, now squaring second equation, what we get? A square equals 3q plus 1 whole square, and we know what is the formula of a plus b whole square equals a square plus b square plus 2ab. So now let's write that. So this will be 9q square plus 1 plus 6q. Right. So can we just write it as 3q square? Just for this 6q we can write it as 2q, and this one will be just left out here, right? So will this whole thing in this bracket, will this be some integer? Yes, of course it will be some integer, right? You put any values, you will be getting some integer for this whole thing. So can we just name it as 3m plus 1? Yes. So we can say that square of any positive integer is either of form 3m plus 1 or 3m, and that's what they have asked in the question, right? Let's see here. They have asked, use Euclid's division lemma to show that square of any positive integer is either of form 3m or 3m plus 1 for some integer m. So I hope you have understood this problem, and fourth problem is also solved. Now let's read the fifth question. Use Euclid's division lemma to show that cube of any positive integer is of form 9m or 9m plus 1 or 9m plus 8. It is same just like what the problem we solved here in the fourth one, but it's cube instead of square which was given in fourth question. So just try solving this question. If you can solve, then very nice. If you could not, then we will discuss this question in part 4 video of this chapter, where we'll be discussing some of the important questions which have appeared from this particular chapter. So I hope you have understood something related to this Euclid's division lemma. And if you have any doubts, please post it in the comment section below. I will try answering them. And thank you.